Hi, everyone. In this set of lectures, we're going to be talking about natural language processing and text mining. We're going to cover natural language processing, rationale for text mining, encoding and internationalization of text, NLP tasks, and text classification and analysis. And some credits information here. Some of the following material comes from University of Michigan's Applied Text Mining course on Coursera. So let's get to it in the first set of lectures. Natural language and text. Natural language is language used by humans, and that is in contrast with artificial computer languages. Artificial computer languages are formally structured in text based on binary data and computer logic. So they are created to emulate precisely the logic of the computer, but facilitate computer operation via something that humans comprehend more easily. So a very common statement in computer language, artificial computer language, is the following: for all items in list, print each item. And that just works well for the computer. Now, natural language is developed organically by humans. It has a formal structure in sound and text, but it is largely metaphorical and ambiguous. So in the statement, "In me thou seest the glowing of such fire," from Sonnet 73 of William Shakespeare, we see this kind of metaphor of the glow of the fire glowing on someone's face. Now, metaphor is really not just a quality of poems. It's all over language if you start to pay attention. I mean, think about pay attention. In paying attention, you don't actually have to pay money to anybody. But we use pay attention in this kind of metaphorical way. Now, language is ambiguous in the sense that there's a lot of information that is implicit and based on the context, based on previous human experience, based on cultural knowledge that does not need to be expressed for others in the same context to understand. This doesn't really work well with language because everything in language has to, in artificial language, everything in artificial computer language has to be explicit. So there is this major difference between natural languages and artificial computer languages. Natural language is also often, of course, spoken, but also written in text. And there's a difference here too, right? Because there is intonation. There's all kinds of characteristics of sound language that may not be represented in text, and vice versa. For example, in text, we may represent something with a period or a comma, which may not exactly be represented in text the same. In sound the same way. But we're kind of using these natural language and text together, as we'll see. So computer processing. Let's recall that all computer processing is based on binary data and strict mathematical and Boolean logic. So the logic that we just saw, the iterative logic for every item, print each item, or the conditional logic of if machine is on, then print the on signal, things like that. So text in computer is represented via binary data. So for example, the letter A will be represented as 1000001, and letter B is represented as 01000001. And that's in the encoding called ASCII II, or ASCII2, or just ASCII, which we will talk about. So natural language processing actually began early with computer development, with translation of a few sentences of text. And there's the famous example when they're trying to do this so-called machine translation of a few sentences from English to Russian. And In the early days, this was based on matching values from an existing dictionary. So for example, if you have recorded in the computer, and this is the computer that was actually used right here, you see there's not even a screen in it, but if you somehow record a dictionary of English and Russian in the computer, so you have, the word thanks in English is translated to spasiba in Russian, then you can theoretically take a sentence and just translate every single word. Take thanks, and then where it says thanks, just write spasiba, and so on. As you can imagine, this doesn't work very well. And although they thought they were going to solve this machine translation problem very quickly after the 1950s, it took much longer to do so, but it is much better nowadays. Just to continue a little bit with the history, an interesting development was ELIZA. ELIZA is actually a computer program that emulates or simulates questions of a psychotherapist. And the original program was described by Joseph Weizenbaum in 1960. But then I think this implementation here is from an update in 2005. So for example, ELIZA would start with some initial start phrases. Is something troubling you? ELIZA is the computer. And then the human being would reply, men are all alike. And notice that we were using keyboards and not voice, because voice creates another level of difficulty in the processing. And then Lisa would reply, what is the connection, do you suppose? And you may ask, well, how does Elisa know to reply, what is the connection, when, say, men are all alike? Well, you can figure out from the formal structure of text and human language. Here we have a term. Usually words are started with a noun and then followed by a verb. And then we also have this adverb here, all, and we have an adjective. So it's a very basic structure of language. It's a kind of description or definition of something. And so a reply about connection is fairly predictable here, because any kind of definition here can be questioned by the connection. So women are all alike, and so on, or other kinds of sentences of this kind can be followed by such a question, and it would kind of make sense. But you can kind of notice that it's kind of like not that specific, but it's kind of interesting. And there is, of course, a set of already pre-created phrases on the computer. There is things related to psychotherapy. So Elisa's, so a person says, he says, I'm depressed much of the time. And then Elisa is programmed to say, I'm sorry to hear that you're depressed. So if the computer finds the word I'm depressed, then the reply is generally going to be, or always going to be, I'm sorry to hear that you're depressed. So that's pretty standard. And now we've come a long way into NLP and text mining. We have written text everywhere on the web, social communication, on Twitter, on Facebook, on Wikipedia. Much of our books are digitized. The newspapers are provided in digital format, and there's a lot of text there. Data continues to grow exponentially, both text and numeric data, data, of course, recorded information. There's some statistics here that might be a little bit dated, but it just continues to grow, and these numbers are kind of not humanly possible to comprehend. Approximately 80% of all data is estimated to be unstructured, text-rich data. So over 40 million articles in Wikipedia, 4.5 billion web pages, 500 million tweets per day, 200 billion a year, over 1.5 trillion queries or searches on Google a year, which is, these are natural language searches, right? So when you search on Google, some people would just, of course, depending on you're searching, you put keywords, if you're looking for fast cars, you just put the word fast cars, but sometimes you will add something more natural language like, so why is the earth round, or something like that, right? So that's what we mean by natural language. Taking an example here of social media, as we may have talked about, there's already information here that it's fairly structured in the platform, and can be might not really be considered unstructured text. So we have social network information, people following, people being followed, how many are followers, how many are being followed, the author or the entity that is running the page, and we have the location here, and we can kind of figure it out because it's already structured in the background. But we also have a little bit more unstructured information within the text of the messages themselves. So in this text here, CDC recommends that certain populations receive a booster shot of Pfizer-BioNTech's COVID-19 vaccine at least 6 months after completion of their 2-dose Pfizer-BioNTech vaccine series. So you might be able to actually find from this unstructured text topic words. So things like booster shot and COVID-19 vaccine, they indicate that it is a topic. Now, how do you know this is a topic? And why is the word recommend not a topic? Well, recommend is a verb. So verbs are usually not topical words. Why is CDC not a topic? Well, CDC is the entity, is the subject of the sentence, is the entity doing things. So we know that it's not a topic. It might be an entity. So this would be another entity, and so on. And there are different approaches to this kind of analysis, but this is the kind of analysis of a textual interpretation, textual mining, natural language processing, maybe a temporal state. So if there's information regarding time, you may capture that from a text based, once again, various approaches, statistical approaches, dictionary-based approaches of matching certain words that are already noted to be related to a temporal state, and so on. So what can be done with text? A lot can be done with text. We can parse text, meaning break it down into different parts. We can find, identify, or extract relevant information from text. So the temporal state, when something happened, when it did not happen, or we can classify text documents. So for example, emails, we can classify, and this is already done in many email systems. So you receive an email, your email program, spam, and you want to identify if the email is a spam or not spam. And there are different ways to do that. That's a text classification task. We can search for relevant text documents. Of course, search engines do this, and you can do this by different ways as well, just matching keywords, but also other statistical approaches for it. There's sentiment analysis, so which is kind of a text classification, identify if the sentiment is positive or negative. And there's topic modeling, which extracts topics from a piece of text, and we'll talk more about this as well. That's it for this one, and I'll see you next time.